All right, welcome to Unit 3, Inverses. This is Day 3, Rational Exponents. So you can kind of see the rule for rational exponents right up here, that when you have b to the 1 over n, you could write that as the nth root of b, but we're going to be focusing on using rational exponents today. So the denominator is always the power of your root. The 1 is coming from the fact that this is b to the first power. Alright, you can see a couple other examples here, but we'll go ahead and jump into this. We're at a to the 1/7 in radical form. The power of the root is 7. It's the 7th root of a to the first power. For part B, since the power of the root is a 2, it's a square root, remember. This will be w to the 1/2. 1 on the numerator because it's w to the first power. 2 because, again, it's a square root, a second root. And there's my answers for A and B. The 7th root of A and w to the 1/2. Alright, on part B, you can actually use your calculators on these problems. I will show you how it's happening by hand real quick. If I have 49 to the negative 1/2, you got to remember your exponent rules, that to apply a negative exponent, you would actually do 1 over 49 to the 1/2. That's applying the negative. Now, that's reciprocating the function, by the way. Now what we're going to do is find something that can cancel out this denominator of 2. So if you'll remember that 49 is 7 squared. Now 7 squared to the 1/2. The 2 times 1/2 will cancel to a 1. So 1 over 7 to the 1. And there you have it. Again, your calculator can handle rational exponents. So if you just type in 49 to the negative 1/2, you would get 1/7. Moving on to part B, 16 to the 3/4. So this is a 4th root is what I'm going to need to do. So I'm going to think of perfect 4th powers. 1 to the 4th is 1. 2 to the 4th is, lo and behold, 16. So I'm going to rewrite 16 as 2 to the 4th power. Still raised to the 3/4. 4 times 3/4 will come to 3. Remember, power to a power you multiply. And 2 to the 3rd is 8. And there's my answer. What this screen here is doing is just kind of expanding it, because you'll see powers other than 1 sometimes. So if it was b to the x over y, that's the y root of b to the x power. Or you could write it as the y root of b raised to the x power. The difference here is that you're taking the root first. Over here you're raising by the power first, but there's no difference between the two. You can always rewrite it how you see fit. Moving on to example 3, though, the formula, the big long formula, can be used to estimate the maximum total mass that a weightlifter of mass b kilograms can lift. I'm going to kind of make a note really quick that m is what he can lift and b is his mass, or her maybe. All right. According to the formula, was the maximum that a weightlifter weighing 168 kilograms can lift. All we're needing to do is put in 168 for B. That's the reason why I made this note of which one's which, is to know what to substitute for. The weightlifter is 168 kilograms. That's B, his mass. So we'll put it in there. And you know what? Since it's already solved for M, I'll just type all this mess into my calculator. So I'm going to go ahead and grab my calculator and type in the 512 minus 146,230 times his mass, again being 168, raised to the negative 8/5. And I get 472 kilograms. It didn't tell us to approximate, but given the context of the problem, if you're into lifting weights, you'll know that the weights only measure to the nearest whole kilogram whenever you're dealing with metric system. So this is a good answer for us. What would have been a much more difficult problem had we been given how much does he weigh given how much he can lift. So if we'd have been given the M value, then we got some work to do to solve this. That's coming later in this unit. Some simplification problems for you. You just got to remember your exponents rule. For instance, if you are multiplying two like bases together, you will take their exponents and add them. So this will be y to the 1/7 plus 4/7. That's actually a really easy problem. So y to the 5/7. And we're done. Moving on to part B. Simplify that. That looks so innocent. What you're going to do is you're going to go and apply that negative exponent to make it 1 over x to the 2/3. Now you might think, all right, I'm done, but you're really not, and here's the reason why. This is an irrational denominator. One of the rules you should have gone over in Math 1 is that you can't have irrational denominators because this is a cube root. You don't want that. We need to make this a whole number exponent on the denominator. Now how I can do that is I'm going to multiply the top and bottom by the same thing, and that's going to be x to the 1/3. Because that will complement the 2/3 perfectly well to make it a whole number. Now my final answer will be x to the 1/3 on the numerator and over x to the first power on the denominator. This is our simplified answer. Alright, when doing a problem like this, I would try typing it in my calculator first before I do a whole lot of work. So I'm going to do the 6th root of 16, and I can do that by hitting math. To do an odd power root here, so we would go to the 5th option in math. I'll type in the 6th root of 16, get it out of there, and divide it by the cube root of 2. Math, there's actually a cube root as your 4th option of 2. And let's see if this comes out pleasantly or not. I don't think it does. Let's try converting into it for a. It didn't. It's irrational, so we got to do the work by hand. Alright, to do that, we cannot divide this right now because we need to get our roots of the same power. In fact, what I'm going to do is, today's all about rational exponents. Let's convert them to net rational exponents. 16 will be to the 1/6 power. 2 will be to the 1/3 power. Okay, now let's work with them. Let's get this 16 down to a base of 2 because I know we can do that. 16 can be written as 2 to the 4th. We did it a little bit ago. Now I'll simplify this numerator, and then the reason why I got to a base of 2 is so I could eventually combine it with this denominator. The numerator is going to look like 2 to the 4 times 1/6, which is 4 over 6. And that's going to become 2 to the 2/3 on the numerator. Now, on my last step, remember when you're doing division, you subtract your exponents so long as you have the same base. So this will go to 2 to the 1/3 because 2/3 minus 1/3. And there I go. The thing I would do, the original problem was presented using roots. So instead of presenting my answer like this, I would actually change it back to being in terms of roots. So the cube root of 2. You can actually check this answer, cube root of 2, by using your calculator. And you see where we got this original answer here, 1.25 blah blah blah. If I type in the cube root of 2, my final answer, I should get that same value. And in fact I do. So there we go. That's a check. The calculator couldn't do the problem, but it can certainly check the problem because I am getting the same value here for the cube root of 2 as I did the original problem when I typed it in. Alright, moving on to the 6th root of 4x to the 4th. What I'll do is I'll write that using rational exponents. Right now 4 is to the first power inside there, so this will be 4 to the 1/6 power. X is to the 4th power, so x to the 4 over 6. Alright, as far as the 4 goes, I can write that as a lower base, again 2. So that's going to be 2 squared to the 1/6. X is fine. What I can do though is where it's 4 over 6, I can reduce that to 2/3. Now let's simplify over here on this number a little bit. I will multiply my exponents. 2 times 1/6 is 2 over 6. And that does reduce to 1/3. And there's my answer, but again, because they gave me the problem using a root, I'm going to convert this back to a root. So evidently we're going to have it under a cube root for both of them. That's convenient. and 2 will be to the first power, and x will be to the second power. So the cube root of 2x squared is how I would present my final answer. That wraps up rational exponents. I know there's probably questions out there, so y'all let me know what they are in class or shoot me an email. Thank you.